And who said carbide or carbine something? Someone said na. So any of you can suggest something? C triple
Nit
bond.
Nitride.
Nitrido, sir. Nitrido.
It's called nitrine. Nitrene, nitrine. So it's C minus actually. Yeah. It's a potent pi donor site. So it always stabilizes metal in the very high oxidation. If you want to stabilize metal in a unusually high oxidation state, you have to use one potent pi donor site. Either metal oxo you have to use. You have noticed the vanadil. Or any high oxidation state metal complex are oxides normally, or you can use nitrine, or you can use imido. Imido of course 2 minus, and nitrine is 3 minus. So if it is 3 minus, that means you will have 8, total 8 minus, and chromium 5, so overall 3 minus, right? And chromium 5 means D1 system. Now the thing is, it's very interesting spectrum. Let us first consider the normal way that this chromium is attached to the carbon center. Na? So carbon does not have any nuclear spin, but see, then cyanide means triple bond N is far away. So that impact won't be reaching over here. What impact would be there? The directly bonded nitrogen over here. The nitrine is directly bonded over here, and nitrogen is a N14. So your 1 and 1 I equal to 1, and I equal to 1 means 100% its abundance. So you will never miss it. That means one line, and if you look at this molecule, it is more or less symmetric molecule except this site. So you will be getting basically one line spectrum would be split into 3 lines, and that is indeed happening over here. 3 lines, 1:1:1 intensity ratio. Okay, don't concentrate on this part first. First, let us concentrate on this section. So if you look at this section, that means one line is being split into 3 lines. And unlike all other previous examples, what we have talked about, this is a unique example. Unique example in the sense the ligand is active ligand, which is directly linked to the metal centers. So if it has been directly linked to the metal center and that has been depicted, so it actually proves why the consideration of crystal field was wrong. You go back to the coordination chemistry early stage, that it says the crystal field theory, na? And then the ligand field theory came into the picture, or molecular orbital theory. Now if you look at crystal field theory, what was the need to the ligand field theory to appear? It appeared as because of the fact the crystal field could not explain the color. Okay, crystal field could not explain the spectral feature. Okay, and magnetism also in some extent. So that's why they felt the crystal field was very good when nothing was there. People used to depend on the valence bond theory, but valence bond theory could not explain between the weak field, strong field, all sort of things. But then crystal field theory came, and crystal field theory was very popular for 100 years. And then slowly people realized that it is not complete. And that's why the modern concept of molecular orbital theory came into the picture. And one of the drawbacks of crystal field theory was its initial assumption. It considered no metal ligand interaction, bonding. It only considers some kind of electrostatic interaction. Ligand comes from the infinite distance and it comes to the metal field, and then some electrostatic interaction between cationic and anionic things takes place, but no orbital overlap. Orbital concept was not there actually that time. So orbital overlapping was not there. So this is one of the examples. I'm talking about one of the pioneering example. Via EPR, one could establish the ligand field theory is the validity of the ligand field theory, where it considered the overlapping, the frontier orbital overlapping of metal and ligand, right? And if it was not there, then this line would not have been split into 3 lines. right? So this line is being splitted into 3 lines because of this interaction. Now, how did you know that in hyperfine interaction, which is very easy to understand because it is considering the same atom, right? But super hyperfine, it is considering the two different atoms. And how these two different atoms would interact? They cannot interact through space, right? They only interact through bond. Now, through bond interaction means that there is some kind of covalency. That is the sharing of the two orbitals, and that's why you get single bond, double bond, triple bond, and all these things. And electrostatic interaction means they don't come very close to each other, but they do come up to a distance through which they can see their face. Okay, so they can interact. That's a electrostatic interaction. It's called cation and anion. But the covalency says no, it is not so. It is actually the overlapping of orbitals. And that's why we call they are within the bonding distance. And bonding distance, depending on metal ligand bonding, if it is a single bond, if it is a double bond, if it is triple bond, accordingly the bond distance starts shrinking, right? Okay, triple bond is much shorter than the single bond. So this is one of the examples which proves the validity of the ligand field theory, fact that the crystal field theory was not correct. Anyway, now what happens? So these 3 lines you are getting because of these interactions, but it shows another 4 lines and smaller 4 lines, and each of the 4 lines, you see, it gets splitted into 3 lines. What is happening over here? That there is one isotope of chromium, that original isotope, I think chromium 54 or 55, I forgotten. So that does not have any I value. So this splitting is only due to the super hyperfine disk coupling. And then what happened? The 10% chromium 53, that is also stable isotope, which is having I equal to 3/2. So I equal to 3/2, only 10%. That means the one line is being splitted into 4 lines, right? And these 4 lines, what is happening over here? Their then distribution would be actually your 10 by 3 by 3 lines, each 3 lines. So 10 by 3, very small lines. And then each of the lines naturally would be interacting with this. Okay, no, 4 by 4 it will be. Yeah. So each of the lines would be again interacting with this nitrogen center, and then you are getting 3 lines. So this strong line corresponds to I equal to 0, the splitting due to the metal nitrogen interactions. And these 4 lines appearing because of the 10% chromium 53 I equal to 3/2, and that ratio would be very small, and which is in fact so. And then each of these lines would be there, the part of the chromium, and there this chromium triple bond nitrogen is there, and that would interact with each other, and that would give you the 3 lines, small super hyperfine interactions for the other isotopes. Okay, now do you have time, or I should stop here?
Sir, our another class is already started.
Hey, it didn't already start, because now it is only 29:30. Okay, see you tomorrow, next day. Bye.
Okay, thank you, sir.
Thank you.